For the second example, the turning moment diagram for a multi-cylinder engine has been drawn to scale 1 millimeter equivalent to 600 Newton meter vertically and 1 mm equivalent to 3 degrees horizontally. The intercepted areas between the output torque curve and the mean resisting torque line taken in order from one end, okay, as 52 positive, that means above, negative 124 below, positive 92 above, negative 140 is below, positive 85 above, negative 72 below, and positive 107 is above. So when the engine is running at a speed of 600 revolutions per minute, if the total fluctuation of speed is not to exceed plus and minus 1.5% of the mean speed, so you take the maximum to be positive 1.5% of mean speed, the minimum to be negative 1.5% of mean speed. Okay, so from this, you can find out the coefficient fluctuation of speed. Then the question asks us to find the necessary mass of the flywheel of a radius, means this would be the radius of gyration, 0.5 meter. So these are the given data. So we have the turning moment diagram here. Okay, so above, below, above, below, above, below, and above. So convert this, okay, the scale, which is 603 degree into Newton meter. So you will have 10 pi Newton meter for each small section of 1 mm square of each area here, okay, is equivalent to this amount. Okay, now what we need to do is the same thing. Let energy at point A be z mm square and then plus 52. And you have plus 52 minus 124, so you have negative 72. Okay, negative 72 plus 92, you will have positive 20 minus 140, so you have negative 120 plus 85, you have negative 35. Then plus, then you plus with minus 72. Then you have negative 35, then plus 107, you have negative 107. Okay, then plus 107, plus 107, you will have z mm square. So you just take the net plus or minus any of these values here. Okay, so you got A to H. So both the example, you can see the initial and the final, they are the same. So it doesn't matter whatever unknowns that you assume at the beginning at point A. So the final ones will always goes back to what you have initially. So that is to convert the revolutions per minute to radians per second. So beta W is the greatest fluctuation of energy. So you take maximum minus the minimum energy. So you have to select from list of values here, which one is maximum and which one is the minimum. So the maximum will be Z plus 52 and the minimum should be Z minus 120. Then multiply by the pi, 10 pi, because you are converting it to Newton meter. You're converting it to Newton meter. So this should be mm square. Mm square on top here, cancel off with this mm square. The mm square cancel off with this mm square. You got your unit as Newton meter, which is the unit for energy joules. So you got 5403.54. So once you have found out the beta W, now what you can do is to find out the I first. It is the moment of inertia. So you have your beta W, your phi, which is 0.03. If you were to take plus 1.5 over 100 of mean speed, minus 1.5 minus negative 1.5 over 100 of mean speed, then divide by mean speed. You should get 0.03. Okay, that is your angular speed. So you get your I, that is the moment of inertia. So since I is equals to mk squared, so we have to find the mass. So the k, which is given 0.5 square, you get a mass of 182.52 kg. So that's for example 2. Thank you. Now the torque of the machine varies in a cyclic manner over a period of 3 revolutions. So we know 1 revolution is equal to 2 pi radians. So 3 revolutions would be equal to 6 pi radians. Now the torque of the machine varies in a cyclic manner over a period of 3 revolutions, that is 6 pi. Now the torque rises from 750 to 3000 Newton meter uniformly during half revolution. So half revolution, that would be 1 pi or a pi. So you have 750 to 3000. It rises from 750 to 3000 uniformly. So that's why this is a straight slanting line. And then only half a revolution, so that is taking up a pi. Okay, and then it remains constant for the following 1 revolution. So B to C is 1 revolution, so that is 2 pi, remain constant here. Then it then falls uniformly to 750 Newton meter, falls to 750 Newton meter uniformly during the next half revolution. So that is also equals to a pi. And then after that, it remains constant for 1 revolution. It remains constant 750 here for 1 revolution. That is 2 pi. So that is the end of 1 cycle, 3 cycles, 3 revolutions. And then the whole thing will repeat again from the beginning. Okay, the cycle being repeated thereafter. So determine the power required to drive the machine and also the percentage fluctuation in speed. If the driving torque applied to the shaft is constant and the mass of the flywheel 500 kg, radius of gyration of 0.6 meter. So based on this, what I have here is the first thing we will find out the total energy developed by the engine first. That is the work done or the energy developed by the engine. So that is equivalent to the area of this whole trapezium here. So that is from A, B, C, and D. This trapezium plus the area of this rectangle here. So the area of trapezium is given as half multiplied by this length plus this length here times with the height of this. So you have 2 pi here and you have 4 pi. So 2 pi plus 4 pi times half, then multiply by the height. So that would be this height here, which is 2250. Okay, so we have 2250, then plus the area of the rectangle, which is 6 pi multiplied by 750. So from this, we have 6750 pi. And from this, we have 4500 pi. So when you add it up, you have 11250 pi Newton meter. Then based on energy balance, now, total energy required by the engine. So have to remember total energy required by the engine usually is measured based on the area under the mean torque line. So initially you won't know where is the mean torque line. So you just assume somewhere in the middle of the trapezium. So this is just an assumption, an early assumption. So this will be your T mean. So the total energy required by the engine will be the area below this whole thing here. So that is based on this unknown T mean initially, multiplied by the base that is 6 pi. Then the total energy developed, which we have already calculated earlier, that is the area of the trapezium plus the area of this rectangle here, will give you the total energy developed by the engine. So therefore, you have Tm multiplied by 6 pi equal to 11250 pi. So cancel off the pi, and then your Tm, that means your mean resisting torque, would be 11250 divided by 6. So you get your mean torque, which should be, okay, your T mean should be how much? Okay, later on. From here, you can see this would be the work done. Then from here, divide by 6 pi. So your T mean would be 1875 Newton meter. This is your work done initially, which is also the total energy developed by the engine, 11250 pi, then divided by this 6 pi here. So cancel off the pi. So you will get 1875 Newton meter. That would be the mean resisting torque. Then converting the speed, which is 250 revolutions per minute. So in this question, it is not stated whether it's max, mean, or average. So usually we will take these 250 here as the average speed. So you take 2 pi n over 60, so you got 26.18 radians per second. So we find out whatever that is required at first. So we know that power will be equal to 2 pi nt over 60, or t, the product of omega t. So omega, you have that is the angular, the average speed, 26.18, multiplied by the torque. This will give you the torque or the power required by the engine. So 49087.5 watts. So the question asks us to find the power required. So that would be the power required. Then after that, that is your moment of inertia, which is equal to mk squared. M would be the mass. K is the radius of gyration, 0.6. So you get I. Then based on the formula that we have, okay, now what is this? Beta W, if let's say, for example, in this diagram here, you can actually find out this area here. Look at my pointer, this area here, and this area here, and also this area. So you can do from what we have assumed at the beginning of the lesson. That means the first example, you can assume energy at this point here be Z. Then minus of this area, then you consider the next point at P, then you have this minus, or this one negative, plus this area. Then when you move up to this point here, you have this one negative, plus this, and minus this area. Okay, if you were to do it in the long way. Otherwise, remember this. The beta W, that means the greatest fluctuation of energy, usually is taken based on the largest area which is above the mean torque line. This is your mean torque line. The largest area above. This would be your beta W, the greatest fluctuation of energy in the short way. Okay? In a long way, then you have to consider area by area. So you have to find out the area of each section. So to find out this area, remember this is a trapezium again. So you can use whatever I have considered on top here. You can consider half multiplied by this length here, 2 pi, plus this length here, which is 3 pi. Is it 3 pi? So 2 pi here. Okay, half a pi here because this is 1 pi and this is 1 pi. So this one, based on the geometry, should be half a pi and half a pi. So you have half times 2 pi plus 3 pi multiplied by 1125. That will give you the beta W straight away instead of following this. Okay, so you will have your beta W straight away as 8835.73 Newton meter. You straight away find out the area of this section which I have shaded. Remember, I repeat, this would be the area of the trapezium, which you have half times this length here, plus with this length, multiplied by this height. You should be getting 8835.73 without the pi. Okay, so which is in Newton meter. So once you have found the beta W, the next thing is the question wants us to find the percentage fluctuation in speed. So that would be the phi. So you have phi beta W, you substitute your beta Wi and your mean speed here. Okay, you should get 0.0762. Then times 100, you will get it in terms of percentage. Okay, that's for example 3 for today. So we will continue during the next lesson. So I would say thank you for your time and stay safe, everybody. So if possible, please do consider subscribing, like, and share. Thank you very much. Bye-bye.